Hi, good morning, and welcome to the ZP Developer Zone webinar. So we'd like to do this webinar every Thursday at 8 a.m. London time, but today we've actually come on a little bit early. I mean, it's mid-August. A lot of people are on vacation, so a lot of calendars are a little bit more sort of messed up than I would otherwise like. So my apologies for coming on like 45 minutes early, but let me sort of go forward really and just there's 5 questions. As always, there's quite a pace, so I'll go forward. Don't forget the ZP Academy. There's at least 2 free courses on the ZP Academy that we put out there. Don't forget our webinars. We do several webinars. I suppose I've forgotten to mention that there's going to be a Julie webinar this month. There's a Sense It All webinar. There's this weekly webinar. There's a special webinar for our collaborators in India. Don't forget collaborations. People do come to us and ask us for collaborations. I do always say it's easiest when there's some funding in place, and that particularly happens in Norway and the UK. Also, we have been hiring of recent. There's a ZP Developer Zone website, and then there's workshops and lots of the questions, especially when the questions become really repeats and some of the questions sort of always around a theme. I say come to the workshops, and I'll mention the workshop several times. So don't forget, we have a workshop in September. We have a really good big workshop in September. It's a 2-day workshop because immediately after it, we also have the Scandinavia Sensor Summit. There's a workshop in September in Coventry. We have a workshop in September in Horton. We do have the Scandinavia Sensor Summit, and also there's a workshop in Grenoble in October. So we do have the Scandinavia Sensor Summit. If you see a link today, that link will definitely be underneath the video. I've already put it on YouTube and put the links underneath it. Question number 1 was double pulsed amperometry. So I will discuss that, whether you let's say, whether you just use a static potential when doing amperometry, or can you do something like double pulsed amperometry. I'll comment on that. The composition of our platinum and gold screen printed electrodes. Originally, I thought this was a question around the composition, but I think it's more really a question about the compatibility of our inks towards things like hydrogels, and I'll comment upon that. Making a capillary fill sensor. Zimmer and Peacock, everything we make is meant to be and is compatible with large-scale manufacturing, and that includes microfluidics. How do we bring a sample to the sensor? So I'll talk about capillary fill sensors. I'll also talk about graphene electrodes. Actually, I just want to make a comment on that capillary fill sensor. Even though we're going to show you today quite a manual process, this is what is done in an automated fashion at scale to make glucose sensors. So I think what's really nice about the Zimmer and Peacock is our technology, especially if you're coming from an academic perspective, is actually showing you what's done in, let's say, when people really want to manufacture this stuff, which is a terrible adjective. And I'll talk about graphene electrodes, and number 5, I will talk about interdigitated electrodes. Good question, actually, number 5, because people like interdigitated electrodes. It's very hard for me to actually think of products in the real world, let's say, that involve interdigitated electrodes. It's really just cost, and I'll comment upon that. So question number 1, double pulsed amperometry. So this person's been asking a series of questions over several weeks, so you keep seeing this theme of continuous glucose monitoring popping up, and in part it's due to this particular questioner who's asking from India. So in amperometry, for example, you're making a glucose sensor. It's a generation 1 glucose sensor. You'd apply 650 millivolts, and you would get a current response. That's amperometry. That's great. If you're unclear about some of this science, come to one of our workshops. We do cover amperometry there. You can also then do pulsed amperometry, PAD, pulsed amperometric detection, wherein in fact the potential is changed. And yes, you will get different signals. And at Zimmer and Peacock, we do this. At each potential, the current response can be indicative of the glucose. It depends on the potential that you use. So, for example, if it's a generation 1 glucose sensor, the potential that you use at 650 millivolts is probably most indicative of the glucose, and a potential step at 50 millivolts on a generation 1 glucose sensor will be less indicative. But you absolutely can use pulsed amperometric detection, and I would actually recommend it. The reason then I can't then go on and say how you interpret it is because it's really specific to the sensor that you're making. All I can say is at a high level, I think it's a really good idea, and actually it's something that we would do at Zimmer and Peacock. Slight rant here, but the days of amperometry are over. And what I mean by that is we live in a world of machine learning. Under that, we have AI. Machine learning and AI, they love features. Amperometry is boring. It just applies a voltage, you get a potential. There's no features. You can't give that to a data scientist and say, give me the best algorithm you possibly can. Once you start adding features, for example, using pulsed amperometric detection, then you're giving your data scientist more features to play with and they can come up with a smarter algorithm. So at a high level, I would suggest it. I cannot give you the blueprint to how to do this because this person's making their own sensor, simply not on the project. I can't see the raw data. I can't see the results of your experiments. So I am just to say, single amperometry, single pulse amperometry is used a lot in industry. These are 3 products in the CGM space, and they all use at least the basis of what they do is single potential amperometry. Obviously at ZP we do have all the formulations so people can make their own glucose sensors. This is the activation solution and the barrier layer, and this is my recommendation on a platinum electrode that people should use if making a generation 1 glucose sensor. It's platinum, which is a good start, and it's fairly low cost for a platinum electrode. This image is one I used last week as well. It's just to say, look, everyone who comes on our workshops makes a glucose sensor, and everyone is successful. It's really great, because so many people, especially on the commercial side of things, talk about CGM, continuous glucose monitoring, and it's just a badge of let's say honor to actually come to a workshop and make yourself a glucose sensor. Anyway, I put a link to that there. Composition of electrodes. So originally I thought that this question was around, and it was what's the composition of your gold and platinum, and will it affect my hydrogel? But later on then they were kind enough to kind of give me a little bit more, and I think they're kind of more sort of thinking, is my hydrogel compatible with your platinum and gold electrodes? So I just brought up this is not all the list of Zimmer and Peacock, but when I look at this list, we have a glucose sensor, oxygen sensor, lactate, hydroperoxide, pH, chloride. Every single sensor on this list is either made on our platinum ink or our carbon ink. So first of all, our platinum inks and our carbon inks and our gold inks, because we do a lot of immunosensors making our gold inks. They've all been used multiple times by Zimmer and Peacock to make biosensors. So I can absolutely tell you from practical experience that we've used our gold sensors to make immunosensors all the time. I'd almost say that our immunosensor hit rate is like 100%. And that's because we're really boring. People say, I want to make an immunosensor. And when I say immunosensor, it could be antibodies, antigens, receptors. We have a formulation. We take the gold, we affix the macromolecule to that gold surface. We often use impedance spectroscopy to read it, and it works because we're very boring and we stick to our formula, but it works. The only thing that varies is the antibody antigen receptor itself. So, okay, those things are variable. Then if we're making enzyme sensors, especially the oxidases, we're always using the same platinum ink, platinum electrode. It's really good to be really boring in life because obviously if your role is in academia, your role is to invent and discover. If your role is industrial bioelectrochemistry, which I would say my role is, it's to make things work and to get things onto the market. So we're always using the same platinum. And then the carbon, the electrode I talk about the most in these workshops is that hypervalue carbon electrode. It's really good because we make it in really high volume. We make it specifically for ourselves, and then we put it onto the web store, and we're selling it on the web store. We put them in sheets, and we call them perforated sheets because you can just pop them out of the perforated sheet. It's like 250 euros for 300, so it's less than €1, less than $1 each. So in your question, no, honestly, you should be able to put hydrogels onto these materials, and if there's something happening, let's say, that's what can I say? I gotta say, that is the challenge of life and chemistry. It's not deterministic. Strange things happen in the world of chemistry and biology. And when I say deterministic, in engineering, if I have if I have a 3D file, I can print it. I might have to do a little bit of optimization, but it will happen. Whereas, unfortunately, in chemistry, you take a solution, you put it on a material, and something strange happens. You've got less direct control over things, so it's sort of not so deterministic. That's what makes science and the wet sciences so hard. Absolutely love our materials. They're completely tested to the nth degree by us in terms of things like hydrogels. We do, in fact, we do use hydrogels quite a lot to immobilize enzymes, for example. In fact, this is a good example here. Anyone who comes on our course, we take one of our electrodes, we use a hydrogel formulation to hold the enzyme in place. We put a barrier layer on top of it. Everyone gets to test it with glucose. We have the reaction, which I go very quickly. And there's a reaction with oxygen. We get hydrogen peroxide and we get a signal. That's an absolute classic. That's one of the slides from our workshops, and then everyone gets to make and do this. You get the theory and then you get the practical. It works really quite nicely. Electrode suggestions. I do say this, that I am trying to persuade everyone to come on to the hyper-value platinum electrodes, because we get the volume and therefore we get the pricing. I tried to convince everyone to come on to the carbon electrodes. This is my favorite electrode by far, because carbon as a commodity material is so low cost compared to platinum. It's sort of night and day, really. And then gold, if people want to make sort of self-assemble monolayers, etc., then the gold hypervalue electrode. So all these links I've put underneath the video already. Question number 3. So this person wants to take a screen printed electrode. They want to put a micro volume sort of chamber above it. They do have a few things here, which is, so they want the micro volume. That's what we call a capillary fill. They want the reference electrode to be silver chloride. Completely fine. They want the counter electrode to be platinum, and they want the working electrode to be carbon or gold. The first thing I want to say about this is, I did say this in a webinar last week, but at Zimmer and Peacock, we often make the working electrode will be carbon or gold or platinum or graphene. The reference electrode will be silver chloride. The counter electrode is silver chloride. Why do we do this? And this is particularly important when you're making capillaries or micro volumes. The quick question is this. When you're on your working electrode, you functionalize that working electrode, you know the electrochemistry it's about to do. Let me ask you a question. When your working electrode is doing the chemistry that you know you want, what's your counter electrode doing if it's made of carbon and platinum? And the quick answer is, you can guess, but you don't absolutely know. Now let me build you another scenario. Rather than using, let's say, I should have said gold or carbon. Let's say, so rather than using gold or carbon on that counter electrode, let's make it silver chloride. So now when I'm doing an oxidation on my working electrode, what's my counter electrode doing? Well, my counter electrode is undergoing reduction and silver chloride is becoming silver. I know what it's doing. The product of that reduction is not a soluble electrochemical species that may diffuse to my working electrode. If I was doing a reduction at my working electrode, what's my counter electrode now doing? It's now doing an oxidation. So silver is becoming silver chloride. That product is an insoluble material that has no chance of diffusing to my working electrode. So what I want to say is this. Don't ask for 3 materials in a screen printed electrode, because what that's going to involve is, first of all, cost. You're going to have to print the silver, you're going to have to print the platinum, and you have to print the gold or carbon. So you've just added cost. If you do, let's say, the counter and reference is just silver chloride, you've just reduced sort of the number of prints required down. So you've just reduced cost. That's good. More importantly, though, when you're in a micro volume, what happens on the counter electrode is really important, because the distances and the volumes, the distances are very short, a few millimeters, and the volumes are something like 4 microliters. So what happens on the counter electrode is really important, because I've seen it where actually you're doing an oxidation, let's say, on your working electrode, the counter electrode is producing hydrogen peroxide, which diffuses in the assay time over to the working electrode and starts oxidizing, which then starts forcing the counter electrode to produce more hydrogen peroxide, which then diffuses across the working electrode. And you've actually set yourself up a feedback loop, a chemical feedback loop, and you get really sort of just drifting signal because this feedback loop is getting stronger and stronger and stronger. The counter electrode is producing more and more hydrogen peroxide, and the work electrode is quite happy to oxidize it. So be careful about mixing materials on a screen printed electrode or having too many materials. You'll just increase the cost by a third. And then ask yourself, it's a small volume, the small distances, do I know what's happening on that counter electrode? Because if I don't know what's happening, it's going to potentially affect my working electrode. In one day, you've made a product on this. For some reason, there's some material gets into that sample that then starts reacting on the counter electrodes and causing you a problem on the working electrode. Stick to something that's deterministic, things like silver chloride. So that's my story on that. Now, your real question is, how do I actually functionalize these materials? Because what they're saying is, how do I functionalize my material if I've got a capillary or a chamber above it? So I will describe that. First of all, my recommendations, because you want gold or carbon, please take the carbon. It's super low cost, but the gold is also an option there. These links are underneath the underneath the video. What we do is we have a special jig. So if you get the perforated sheets, this means that you can essentially take out one electrode or actually just make a row, which is good, because then what you would do is you pipette onto the working electrodes. For example, this is one way of doing deposition, just pipetting on, and then you can put that strip into this clamp, and we sell a kit where you can actually clamp this together and it will make you the capillary chamber on top. But the short answer to your question is, we put the functional material onto the working electrodes, and then we put the capillary on top of it. We don't add the materials after the capillary is on. And like I said, when I was introducing this webinar today, I said the nice thing about Zimmer Peacock is we're showing you what really happens in the real world. This is how a glucose strip is made. So that's for free. Question number 4. I do like, people inquire about our graphene electrodes, let's say. We do have a graphene electrode. Let's mute it here. So I'm comparing here our hypervalue carbon electrode. This is actually the hypervalue graphene electrode. I wanted to bring the video in because sometimes people say, well, graphene doesn't withstand screen printing, and I think that's generally true. But I know this is graphene in part because it's got a very kind of grey, silvery sheen on it relative to the, let's say, the graphite electrode, and that's because of the sort of metalloid. Well, no, metalloid is not the right term, actually. I mean, carbon in general is a bit of a metalloid, but that sort of sheen is because of the sort of delocalization of the electrons, let's say, across the graphene sheet. So the one thing I can say about our electrodes is, and we do get multiple orders on this, it is a very manufacturable process, which unlike a lot of graphene, the thing about graphene electrodes and graphene, especially people are very interested in GFETs these days, is they're just really expensive. But here's a super low cost graphene electrodes, and we do sell quite a few of these, and I think we do different pack sizes. I think there's a pretty decent price on the 200 pack size. Question number 5. I'm just trying to remember myself. Oh yeah, interdigitated electrodes. So I get it. When people are making gas sensors, one way of reading a gas sensor is a kind of chemi resistor where you have a couple of electrodes that are isolated from one another. You put something like a solid electrolyte over them, and if you're trying to kind of detect things like hydrogen, carbon monoxide, etc., nitric oxide, you will get a change in resistance, which you can measure sort of through a current, for example, when the gas is present. Absolutely understand it. Interdigitated electrodes often are quite expensive to produce. Very small feature size on I wouldn't say exotic material. Silicon's not an exotic material, but you only get low price on things like silicon and glass wafers if you're going to do super high volume. And there's really nobody doing super high volume. If you look at the, there are glass interdigitated electrodes available on the web, but those companies that are producing them are literally selling them at cost. There's hardly any margin in them for them. So it's not scalable. That the cost that you're seeing for the R&D costs you're seeing, or the R&D pricing, there's literally no margin there. So it's really not a scalable technology. But we actually make gas sensors on our hypervalue carbon electrodes. So I just want to touch upon that a little bit. We would take our hypervalue carbon electrodes, because I'm making a chemi resistor here. You can do when you're doing resistance or impedance measurements, you can do a 4 probe or a 2 probe. I'm really talking only about 2 probe. But we would put like our solid electrolyte between maybe these 2 electrodes here, or we would do it here. I would actually try both. And the nice thing about the cost of our electrodes is you can actually try both. And I only need to use 2 electrodes at a time, even though this is set up for 3 electrodes. So if I was trying to make a chemi resistor, even though not all the literature, but a lot of the literature says, interdigitated electrodes, this is really a sort of theory-driven practice. But in practice, when you're really taking into account things like, actually, can I ever scale and make a product out of this? It's just as well to use some of these more macro electrodes. You don't need this highly interdigitated electrodes. You'll get a perfectly decent signal out of this. And in the end, a lot of science, especially if you're making gas sensors, it should make its way into the real world. Otherwise, it's just going to remain in the papers. Well, if it's going to make its way into the real world, it needs to be at a low cost, and these electrodes are a low cost. I've also put equipment here. Now, this person probably has an impedance spectrometer, so they might not need it. These are the carbon electrodes. I have put a link to this, hopefully underneath the video. What they will need, this is the cable. This is the cable. It's got a LEMO plug on it, and it ends in banana plug 2mm. So the LEMO is what we call 5-pin. This will work on our Anapot EIS. The most important bit really is this connector. This connector, we have connectors with 7mm slots on them. That's good because that will work with our 7mm screen printed electrodes. On the back side of the connector, we have orifices or holes for either 2mm, 3mm, or 4mm banana plugs. You have to look at your potentiostat and say, is it a 2mm? So if you've got a palm sense, they're generally 2mm. I think Autolab, for example, is 4mm. So you have to make that choice. But hopefully, I'll put this link underneath the video. So that connector is super important. Otherwise, if you don't make, especially when you're doing resistance impedance measurements, if you don't make a decent connection every time and a repeatable connection, it'll be part of your signal that'll really confuse you. So question number 1, at a high level, I absolutely do recommend actually you go for double pulsed amperometry. But seriously, I can't absolutely advise you because I don't know your electrodes. I can't see your data. But at a high level, I would actually say it's a good idea. This was not so much a question about actually our platinum gold electrodes. It's actually whether they were compatible with, I would describe them as hydrogel formulations. In our hands, they absolutely are. And actually, I don't want to be hyperbole on this, but easily, we spent hundreds of thousands of hours doing those kind of formulations on top of our on top of our platinum and gold electrodes. Making a capillary fill sensor. We have a kit. So you can buy one of our sheets. The sheet will be what we call perforated. You can pop out a row of electrodes. You functionalize them maybe by hand because you don't have a robot at the moment. And then you put them into the clamp, and the kit comes with everything pre-cut, and then you seal it all together. So hopefully there's a link underneath that video. The graphene electrodes, absolutely, we have a graphene electrode. I'd sort of say to people, look, the price is so low, just try it or buy it and try it, see if it works in your applications. On the interdigitated electrodes, I just think that interdigitated electrodes, let's say they gave you the best results in the lab. That's fantastic. Write the paper. But in the paper as well, also put a chapter in or a paragraph in that says that we also tried, more macro industrial scalable electrodes, and we, let's say our results weren't as good, but at least it still works. And you could say, your conclusion would be interdigitated was best. We tried these also screen printed electrodes; they were also working. And it's really for the commercial team then, whoever, let's say, licenses this, to make the decision which way to go. But I would include that in your paper as well, and be really careful about thinking that there's only one solution to chemi-resistor gas sensors. It's interdigitated electrodes. It's really not. We do this all the time. And then I want to say thank you. So first of all, apologies, I went early this week. It's just there's a lot of vacation season going on in the UK, and otherwise, we do have, in fact, I've got it linked here. We do have a contact page on our website. People post questions. The questions get looked at, and we prepare slides every week to answer those questions. So please don't hesitate to reach out to us. Okay, thanks very much.